colleague Stan Leisink is not able to join, so I have to do it on my own, which is no problem. Before we jump into the entity deduplication, I would first like to sketch the context. So we as banks do not only have the obligation, the legal obligation to monitor transactions of our own clients, but we also are required to monitor transactions that pass by our bank. We as a large bank have connections with many banks in the world, and the smaller banks do not have these connections. So they basically use the larger banks like ING to perform international transfers. So these transactions are transactions mostly from people that are not clients or companies that are not clients of ING. So it's a hard task to do monitoring of these transactions because you don't have much more information than only the transaction details. And that's where the deduplication enters. So all the transactions from the same company need to be combined in order to create features for a model to detect potential risky companies. And the challenge is which transactions belong actually to the same company. Companies can have different banks, different bank account numbers, but most importantly, the company names and the addresses can have different notations. So a simple drop duplicates would not work. And this is called deduplication. So the challenge is to identify a single real world entity from multiple different notations. And to show you how challenging this task is, let me show you the results if you type ING in the Dutch Chamber of Commerce website. These are on the right of the screen, you see the first results that you get. So first you get ING Bank, then ING Group. Then there are a couple of, I think self-employed people who are engineers. ING is also the abbreviation of engineer in Dutch. And then somewhere at the end, you see ING Bank again, which is us. So here you see that it's not super trivial to just do a Control F on ING, so to say. There are two difficulties in deduplication. First of all, how do you compare strings? And the second problem is the n-squared problem. Let me explain them both. So there are many string similarity metrics. The most famous one is the Levenstein ratio, but basically all these metrics calculate differences or similarities, as you like, based on the number of character edits that you need to make to convert one string into the other. Let's go back at the example from the previous slide. So here you see two instances from the Dutch Chamber of Commerce. One is ING Bank NV, our company, and the other is ING A Klein BV. And let's take the most famous string similarity metric, which is the Levenstein ratio for both. So you see that ING A Klein BV and ING Bank NV have a Levenstein ratio of 0.625, whereas ING and ING Bank NV, which is basically the same real-world entity, have a lower Levenstein ratio. That means that this ratio gives a lower number, so less similarity for two strings that are actually belonging to the same company. So the main message here is that there is no single string similarity metric where you can set a threshold and say above this threshold, two company names are the same, and below they are different companies. So that's the first problem. The second problem is the n-squared problem. If you would naively compare all the combinations of strings that you have in your data set, the computational burden blows up very quickly. Especially when you work in a bank like we do, we have many transactions. And if you would compare them all individually or pairwise, that number would blow up and it would not be possible to calculate. The Dedupe Python package basically solves these two problems. Dedupe is a package that's open sourced by Datamate, a US-based company, and you can just pip install it in Python. From a user perspective, it works as follows. You provide a data set, you choose the columns that you want to use for deduplication, you choose the string similarity metrics that you want to use, and then you enter into an online learning session where you manually label pairs as a match or as not a match. And then Dedupe is trained and it generates deduplication results, basically indicating which company representations belong to the same real-world entity and which others as well. Let me now explain what happens under the hood of Dedupe. So the first thing that Dedupe does, it applies blocking rules. So there is a list of, I think, more than 50 blocking rules, and these rules are the same first word, the same first 3 characters, the same integers. And those blocking rules are applied to all the strings that are in the data. And then the smallest set of blocking rules that obeys this manually labeling from the previous slide, that is kept. And for this, for determining this set of blocking rules, a greedy set cover algorithm is used, a branch and bound algorithm. We don't go deeper into that. The advantage of applying these blocking rules is that you only compare strings that belong to the same blocks. So here on the right, you see some basically fake data that I created myself. It's just the Eurostoxx 50 companies, and then different ways of representing their names and their combined with their addresses. If you would naively compare them all, you would have to do this for all the orange blocks. If you apply blocking rules, so let's say you only compare the ones that have the same first word, then you see the number of comparisons that need to be made is much smaller. So this blocking solves the n-square problem. The other problem was about scoring, about how to determine what the similarity is between the 2 strings. As I said, Dedupe allows you to provide the string similarity metrics that you want to use in your deduplication process. The package is shipped with 2 string similarity metrics, the normalized defined gap distance and the conditional random field distance. And we have used both. Moreover, we added 2 string similarity metrics that work on a token level instead of on a character level. And these are the token set ratio and the token sort ratio, which are implemented in the famous Python package called fuzzy-wuzzy. Then these 4 string similarity metrics are calculated for each pair of strings in the blocks. And these enter into a simple logistic regression model. So let's have a look on the right side of this slide. So we have 2 pairs of strings, ING Bank NV, and ING Bank and UBS. There we have the 4 string similarity metrics, the affine cap distance, the conditional random field distance, the token set ratio, and the token sort ratio. These are just 4 numbers, and those 4 numbers are the features for this logistic regression model, which would give a high score, a high probability of being the same company to the pair ING Bank NV, and it would give a low score for ING Bank and UBS. So far, not too exciting, but this is where the magic happens in the Dedupe package, and I think it's really smart what they made. So what they do is you now have for each pair of strings, you have a probability from the logistic regression model. In the Dedupe package, a big graph is made where the edges between the nodes are the probabilities from the logistic regression model. The nodes are the entities or the representations of entities that you want to deduplicate. And the first thing that is applied is that there is a connected components algorithm is applied, which is basically an algorithm that splits the whole graph. You should see this as one graph. It would split it into subgraphs that are not connected to other parts of the graph. So in this case, we would have component 1. These are the things with Banco in the name. And a component 2 would be the cases here with Airbus in the name. Then for each component, hierarchical clustering is applied to the graph. So in component 1, we have all the Banco, the string starting with Banco. And here a threshold is applied in the hierarchical clustering, and this is where the actual deduplication takes place. So basically, this is where the distinction is being made between the Banco Bilbao's and the Banco Santander's. At the bottom, in component 2, you see that everything falls below the threshold. So basically, all the Airbus strings belong to the same company, being Airbus. Let me show you on some data how this would work on how this would work in practice. I share a demo that I prepared. I hope you can all see it. So we are going through all the steps of the Dedupe package on this data set that I prepared based on stocks 50 companies. So we start with a data table, just a row number and the name with the address included of those companies. The first thing is that Dedupe applies blocking rules, and the blocking rules that it found is basically one rule that combines two, they call it predicates. The first one is the first token, so that's basically the first word of the string, and the second one is the first 5 characters of the string. And those blocking rules are applied to all the names and addresses. And then the combinations that end up in the same blocks are compared. So here we have the block data. Here we have the first block key, that is the first token. Then a colon, and then the second block key, that is the same 5 characters at start. And that is blocking rule 0. There's just one blocking rule here. And that is then calculated or assigned to each of the rows in the data set. Now let's have a look at some examples. In the stocks 50, there are a few companies that start with Deutsche. Those companies are Deutsche Post, Deutsche Börse, and Deutsche Bank. Oh, Deutsche Telekom, sorry. So here you see some examples of these companies. And yeah, because they all start with Deutsche, they all have the same first 5 characters, so they all end up in the same block. So for all the pairs that you can make, you only see 5 here, but there are many more. The string similarity metrics are calculated, so those 4 values, and the logistic regression probability that 2 strings belong to the same company is also calculated, and that's shown here in the score column. Then these probabilities so these names and probabilities end up in the probability graph, and that is the graph that you see here. And this is where I think the cool things happen. So here you see the edges show the probabilities from the logistic regression model. And here you see that the algorithm is correctly able to deduplicate the Deutsche Börse strings in one group, the Deutsche Telekom strings in one group, and the Deutsche Post strings in another group. And there are some interesting things to have a look at, because you see here that Deutsche Post, this one on the top left, and this Deutsche Börse, it has a probability of 0.7 that these are one company. So if you would just apply a threshold on probabilities, you would deduplicate them together. But because you apply this probability graph, and because you apply the hierarchical clustering on it, there's also the probability calculated between those two. And these are this probability is much smaller. Moreover, the probability of this Deutsche Börse and this Deutsche Börse Frankfurt is very high. It's 100%, it's 1. So because this probability is so small, these two are also not combined. So it basically uses the information from all the graph, from all the connections between the representations of companies to decide on how to deduplicate. So I think this is a very, very interesting example. Another example, there are 2 companies in the stocks 50 that start with Bayer. One is the pharmaceutical, and the other one is better known as BMW, this one. If we look at the probability graph here, you see that this one, this pharmaceutical Bayer, has only a probability of 0.46 with the other one. But because they are so strongly linked to a third one, these two are also combined together. And there is no link at all with the BMW here. Does it always work? No, sometimes it doesn't. Let me show you an example of that. The 2 Dutch companies that start with Koninklijk, which means royal in Dutch. Let's give it a second. Yeah, here you see an example that it doesn't work. So this representation of Koninklijke Ahold is not matched with the other 2 because the probabilities are here just too small. I have to say that in this example, I didn't train it so thoroughly because I wanted to have such example in the demo. Let me go back to the presentation again. And then I explain you what we have done to make this work at scale. So let me summarize Dedupe again. So we have the blocking rules that's first applied. Then within the blocking rule, within the blocks, we have string pairs. We apply the string similarity metrics. Then those 4 numbers enter into the logistic regression model. 1 single probability per pair is the output. That is in turn translated into a probability graph. We apply the connected components algorithm there. And in the end, in the hierarchical clustering of these connected components, of these components, the actual deduplication takes place. So in each of these steps, we basically took parts of the Dedupe package and put that into Spark to make it work at extremely large scale, like millions of rows. In the blocking phase, we distribute blocking over all Spark executors. This operation is independent, so we could distribute that over the executors. And creating the pairs requires inner joining the result of the blocking table. So you see an example here, Airbus ends up in block Air. Let's say that you have a blocking rule of the first 3 characters. Then Airbnb also ends up in that block. This is not a Stocks 50 company, but I needed a company starting with Air for the example. Then the Banco Santander, Banco Bilbao, they would also end up in the block BAN. You would create an inner join, and then you would end up with the pairs table that you see here. So for all these pairs, you would have to calculate the string similarity metrics and the scoring. So that's the next step. And this step, we again distribute over the executors in Spark. And to benefit here from parallelism, we increase the number of Spark partitions significantly. So we broadcast the string similarity metrics to the executors. We also broadcast the logistic regression model to the executors and calculate it on all these executors and then collect it again. Something else that we did here, which is not part of the standard Dedupe package, is that we remove the pairs that have a low score. If you look at the graph here on the right, or the bar chart, the majority of pairs is not a match. That is trivial. That's what you would expect. And the probabilities that are smaller than whatever 5%, there is really no chance that those pairs end up in a deduplicated entity. So we just throw these away. Then we throw these away. Then in the next step, creating the graph, applying connected components, and apply the hierarchical clustering. This we do locally, so not on the executors. Dedupe uses the NumPy memmap, which is basically writing an array to disk to prevent memory issues. And to fill this memmap efficiently with data, so basically the data that's on all these executors in the Spark cluster, we reduce the number of partitions significantly before creating the memmap. This results in shuffling in the Spark cluster, but because writing this memmap is time consuming, reducing the number of partitions before doing that is appeared to be efficient. So in this way, we were basically able to use the Dedupe package, which is created for local work, to the Spark executors and apply deduplication at scale for transactions in correspondent banking chains. I hope there are some questions.
Yes, thank you, Frits, for your presentation. We actually do have some questions in the chat, so let me start. Thomas asks, how efficient is the Dedupe package? What was the maximal data set that you were able to process?
So let's start with the final question. The maximum data set is just all data that we had in scope for a particular project. This is in the order of magnitude of tens of millions of rows.
Okay, thank you. Then we have another question. Is this an interactive Streamlit app where we're looking at for the demonstration of the correlation between entities like Bayer and Koenig?
Yeah, it is. Yeah, short answer. It is.
Okay. Then, well, you have actually some compliments, very clear presentation. Thank you, very interesting. And also three other questions. First of all, did you look at human inference?
Human inference. I'm not sure if I really understand the question.
Or maybe it was still related to the previous one.
Yeah, so probably I should explain a bit more. So there is no training data set. So there is not a large data set that you manually label, throw into the package. So it's really this interactive labeling session. So you provide a large data set without any labels. And then the Dedupe package, it organizes an interactive shell session where you have to respond yes or no to pairs, whether they are a match or not.
Okay, thank you. Then you have another question. What data set do you train on? Names on ING transactions that you know have a match?
No. Well, first of all, that's what I started with in the presentation, that this is explicitly for cases where these are not ING clients. Because if they were ING clients, we would know much more about them. You know, we would just be able to combine their transaction based on their account number. So this is we need to have explicitly not ING clients to apply this deduplication. And it's really interesting because the representations are sometimes really messy. So sometimes there's really bad structure in the transaction details.
All right, and you have for now one last question. Simon says, thank you for sharing, Frits. What process do you see to come up with blocking rules? Yeah,
so these blocking rules, this is part of the implementation of Dedupe. And what they do in the package is they use a greedy set cover algorithm, this branch and bound algorithm, to come up with a set of blocking rules that leads to the minimum number of blocking rules that maximizes the answers that you gave to the questions during training, such that all the pairs that should belong together in the blocks are ending up in the same blocks.
All right, and then, well, actually, one last question. You are working only with unsupervised data sets? That was more like a statement.
That is a very broad question. No, of course not. No, because obviously, when it's about first of all, when it's about telling the algorithm which pairs belong together, that is not unsupervised. And also when it comes to the step afterwards, where we create features and where we train a model to detect potential risk companies, there we need to label data, of course. Yeah.
All right. Well, that was actually the last question, and I would like to thank you, Frits, for your presentation.